And next we're going to have Jonas Hinrichsen, apropos of Sam's question, talk about dependent session protocols.
Thanks. So hello everyone, and greetings from Denmark. I hope you're all enjoying your time in Seattle. So I'm going to talk about our paper, which is titled Dependent Session Protocols in Separation Logic from First Principles. Now this is a separation logic proof pearl. So the first step of any good talk is to understand what is the title even meaning. Now these dependent session protocols, as you will see momentarily, are a reasoning methodology for verifying properties about message passing programs. So let's start there. Message passing concurrency, as we've already seen, is a nice, well-structured approach to writing concurrent programs. In this setting, we often consider threads as either services that expose some functionality or clients which consume that functionality. This is a paradigm that is used in many state-of-the-art languages, such as Go and Scala. One approach to message passing concurrency is that of bidirectional session channels, which use the following three primitives at its core. We first have new channel, which creates a new channel, returning two channel endpoints, C1 and C2. You can then have send, which sends a value over the channel endpoint, and on the other side, receive, which returns the next inbound value in order and returns it. Now, this being bidirectional, you can of course send and receive in both directions. An example of a program written with this variant is the following. Here we first create a new channel, returning the two channel endpoints C1 and C2. We then fork off a service thread, acting as like a +2 service. In the main thread, we first send the number 40, which is received by the forked off service thread, which then adds 2 to it and sends it back. Back in the main thread, we then receive the result, 42, and finally use this assert statement to assert that it is indeed 42, otherwise we would crash. So the goal of this line of work is that we want to prove crash freedom, i.e. safety, but also verify that these asserts don't go wrong, which is functional correctness. Now, as we all know here at ICFP, a way of proving safety is by using type systems. Now, you can go further and get some level of functional correctness by using refinement types and stuff like that, but going all the way, we quickly end up with program logics where we can prove much more rich properties such as functional correctness. The trade-off here is, of course, that safety we can usually prove with automatic checking, whereas functional correctness is something that we need to prove with manual proofs. In the message passing setting, for safety, we have the state-of-the-art session types, whereas the functional equivalent, at least one functional correctness equivalent, is dependent session protocols, which was originated from a work called the Actors Framework. An example of either of these are the following two types, or protocols, as we might call them. On the session type side, we first say that we will send some integer and then receive some integer. Conversely, on the program logic side, we say that we want to send exactly the integer 40, followed by receiving the integer 42. Now, in the realm of functional and program logic pearls, we often want to find sort of the minimal approach to achieving these solutions, because it lets us more clearly understand what is the minimal requirements. Now, such minimal versions exist. One notable is, for session types, one notable such version is by Kobayashi and Darda. However, on the flip side, Actress does not have such a minimalistic version. In fact, Actress employs some pretty heavy machinery. The goal of this work, and thereby this talk, is exactly then to come up with such a minimalist version. Now, to do that, we first need to understand what are the features of Actress actually, so that we know what we need to obtain. Let us first reconsider our program, example program. For this, we can have the two following channel endpoint ownerships, which are propositions in our separation logic, that capture that the channel endpoint C1 and C2 respect the following protocols that notably say that we first have to send the number 40, after which point we can receive 42 and vice versa. Now with this, we can in fact verify that our program is both safe when it comes to the structure of our communication, but we can also assert this or verify this assert statement. However, this is quite a limited protocol. In particular, if we look at the service thread, this thing holds for any possible number, but with these protocols, we can only verify 40. Actress solves this problem with so-called protocol binders that we can associate with each of the exchange messages. The idea here is that the sending side will instantiate these binders, whereas the receiving side will abstract over them. Note also that these binders are dependent, which means that even the tail here can talk about the binders that was previously instantiated. While this is nice, we might get into even more complicated programs, such as the combination of message passing and shared memory concurrency. Consider this following program, which is the aforementioned program decorated with references. In particular, we first allocate a reference to 40, send it over the channel. In the forked thread, we await the reference, add 2 to it, and then send back this unit flag indicating that the reference has been updated. Back in the main thread, we receive the synchronization flag and assert that the reference is now 42. Actress also supports this behavior using so-called protocol propositions, or rather protocol resources in the realm of separation logic. We capture these with these curly braces, in which we can describe resources that is also associated with the exchange of the message. In this case, we delegate this so-called reference ownership that captures that we have exclusive reference ownership over the reference and that it points to some value x. This is very much like a linear type for mutable references. Beyond this, Actress has many more features. It is built on top of the Iris higher-order concurrent separation logic, which gives us a lot of additional reasoning patterns. It has a lot of advanced message passing features, such as channels as messages, recursive protocols, and subprotocols. And it is fully mechanized in Iris on top of Coq. So the motivation is, once again, that Actress is founded upon some heavy machinery. In particular, it is implemented with custom bidirectional buffers. Its protocols are achieved with a step index recursive domain equation, and specifications and proofs are carried out using high-order Go state. Now, for those who are not familiar with these terms, they hopefully sound sufficiently scary. The question at hand is then, how far can we get with a simpler approach? In particular, we want to start from first principles, using mutable references as opposed to bidirectional buffers, higher order invariance instead of custom recursive domain equations, and first order Go state instead of high order. Now, all of these features are readily available in Iris, which will be the foundation of the work. The key idea at hand is then that we want to build one-shot channels based on mutable references and provide the specifications based on high-order one-shot protocols, which are built with Iris's high-order invariance. We then want to build session channels on top of our one-shot channels, which follows the work of Kobayashi, Darda, and friends. And then we want to obtain these dependent session protocols by nesting the one-shot protocols. Finally, we want to mechanize the whole thing based on the existing Iris mechanization in Coq. The contributions are then exactly a 3-layered approach to the implementation and specification, starting with one-shot channels, then functional session channels, finally imperative session channels, a full recovery of all the specifications of Actress, and doing all of this in a minimalistic mechanization in less than 1,000 lines of Coq code. So in the rest of this talk, we will go over these 3 layers, then briefly cover some of the additional features we don't have too much time for, and finally conclude. So we start with layer 1, the one-shot channels. The implementation of these is somewhat canonical. We first have new, which creates a new channel by allocating a new reference to none. You have send, which sends a value by updating the reference to sum of v. And you have receive, which loops until a value has been sent, after which point it frees the reference and returns the value. With this API, we can write an example program such as the following, where we first create a new channel, then in the forked thread, we create a reference to 42, send the reference over, and in the main thread, we await the reference and assert that it points to 42. So the first thing we want to do when obtaining specifications for these channels is to consider the protocols and channel permissions. The protocols have 2 constructors. You can either be a sending protocol or a receiving protocol, and then you have a higher order predicate phi that dictates what the resources that the value has to govern. We have a notion of duality with which you flip the sends into receives and vice versa. And then we have this permission ownership, which is a logical proposition that captures that you are allowed to use the channel endpoint C in accordance with the protocol P. With this, we can obtain the following Hoare triple specifications. First, the specification for new says that we can always create a new channel, giving the true precondition. The result of this is a new channel, along with two permissions, one for free to pick protocol P and one for its dual. What this incidentally means is that one permission will be the sending one and one will be the receiving. The spec for the sending on a channel then requires that we have the sending permission and that we prove that the predicate of the protocol holds for the exchanged value. Conversely, on the receiving side, we need to be on the receiving permission to have the receiving permission, and the resulting value will then satisfy the predicate as described by the protocol. With these specifications in hand, we can in fact prove our example as follows. We pick a protocol which captures that the exchange value is indeed a reference that points to 42. We can then use our specification for true to instantiate a new channel, obtaining the true dual permissions. We can satisfy the send instruction as we can satisfy the protocol predicate with the reference ownership that we obtained from allocating new reference. And we can prove this assert statement based on the received predicate that we get from the received specification. Now, to wrap up the one-shot channels, the question remains, how do we actually prove our specifications? And the crux of this is to come up with a good definition for the channel permission. Now, to do this, we follow the standard methodology of Iris, which is that we first model our channel as a state transition system. Recall that we have three states. First, when we allocate our channel, then once we have sent, and finally when we are received. Secondly, we want to capture each of these states as a disjunct of an invariant proposition as follows. Next up, we want to determine the resource ownership that is captured by each state. First and foremost, the first state has to capture that the channel is indeed a reference that points to none. The second state captures that the channel endpoint or the channel reference now points to some value. And the final state captures nothing since the reference will have been deallocated. Secondly, the second state asserts ownership of the predicate for the value described by the protocol. Then we want to encode the valid transitions of our state transition system via ghost tokens. That is, by including this sending token in the second state, we assert that we can only go from the first state to the second by giving up this token. And with a similar approach, we can restrict transition from the second state to the third state by only being able to only be available to actors who can give up the receiving token. Now, the final step is then to give access to this invariant to the sender and the receiver along with the respective token. We do this by simply including it using this Iris invariant proposition. This effectively captures that the proposition at hand holds throughout the rest of the program, along with either the sending token or the receiving token based on whether you're the sender or the receiver. Now with this, proving the specifications is somewhat straightforward as there is a very clear one-to-one correspondence between this encoded state transition system and the actual specifications. With this, we have wrapped up the one-shot channels and we can now put them into a black box and now focus on layer 2, where we want to implement our functional session channels. Now these channels, being inspired by the work by Kobayashi, Darda, and friends, first use the exact same notion of channel allocation. That is, new simply uses the new of the one-shot channels. Sending will first allocate a new one-shot channel, and then the value that we exchange is in fact a tuple consisting of the payload value v and the channel continuation c prime. After that, we simply return the channel continuation. The receive function is also exactly the same as the one-shot channel, except now we can leverage the fact that we will always receive something of a tuple as captured by the send function. Now what we get with this implementation is a emerging polarized bidirectional linked list. We can illustrate this with the following sequence of exchanges. Consider a thread 1 and thread 2 that initially points to the same one-shot channel. First, we'll have thread 1 send 0 over the channel, at which point it allocates a new one-shot channel that itself points to. We can do this again by sending 1. And now, with this structure, we have implicit asynchrony, which means that thread 2 can already now start receiving the values that we have previously sent. And then we can continue this iteration until we reach this equilibrium where both of the threads now point to the same one-shot channel. At this point, the polarity may flip, at which point thread 2 can now send 3, which thread 1 can then receive. This means that we have effectively obtained these session channels with bidirectional communication. The only crux of using these is that no channel sends at the same time, which is an underlying property of the specifications given to the underlying one-shot channels. So all that remains is to come up with these nice session protocols to appropriately ascribe the values that we actually exchange. The first step towards this, we can consider the following simple protocol from the introduction, where we just want to ascribe the value. First, we have this exclamation mark, which states that we're a sending protocol. We then use this syntactic sugar to say that the value we exchange is in fact a tuple consisting of the payload value v and the channel continuation c prime. The first part of the predicate then captures that the payload value v is exactly the value w dictated by the protocol. The second part then states that the exchange channel continuation c prime follows a protocol corresponding to the tail of our session protocol. Now this uses a dual, and that is because if you look at the implementation of send, we want to return a channel continuation, which at the end of the day should follow our own tail, which means that the channel continuation that we sent over the original channel would have to be its dual. However, as pointed out in the introduction, these protocols are a bit too simplistic and we would like something more expressive. We can then achieve the appropriate dependent session protocols as follows. In particular, we encode the binders using an existential quantification inside of our predicate. We then feed this quantified value into each of the protocol constituents, which are treated as closures. Additionally, we simply include the proposition captured by the session protocol in our original one-shot predicate. Obtaining the receiving corresponding side is then simply a matter of taking the dual of our sending protocol while also dualizing the tail in order to cancel out the dual that is inside of the one-shot predicate. With these definitions, we can arrive at the following specifications. The specification for new is exactly the same as for one-shot protocols. We can now simply use these more rich dependent session protocols for the protocols. The specification for send is also quite similar. We can only send over channels that are in fact sending channels or sending permissions. To send, we still have to give up the ownership now specified by the protocol of the session protocol. We can only send values according to the protocol, and the result is a channel continuation, which we can then operate over according to our tail. Finally, the biggest difference is this T here, which is the term instantiation picked by the user for the session binder, the protocol binder. As for receive, this follows the same structure as well. We can always receive on receiving permissions. And as for this postcondition, well, if we unfold the receiving protocol, we can see that these correspond exactly. Now, this might not seem entirely obvious, but at least it does feel quite canonical. And the foundation for this canonicity is that we have these higher order one-shot specifications. In particular, the crux is that our dependent session protocols rely on the higher order invariance of iris. To make sense of this, recall the following definitions. First of the channel endpoint permission and the sending protocol, and then the following unfolding in which we first unfold the channel permission, thus revealing the underlying invariant. then unfold the sending protocol, revealing the underlying channel permission. And finally, we see these invariants inside of invariants, which is only made possible by the high order nature of Iris. But once again, these are readily supported, so we're in the clear. Once again, we wrap up this layer and continue with the third and final layer of imperative channels. The problem at hand is that working with the functional channels is quite inconvenient, as we keep having to parse around this channel continuation. Instead, we want something more imperative where we can just work on the same channel endpoint. We can achieve this quite immediately by simply wrapping each endpoint within a reference and then updating the reference in accordance to the current channel continuation of that endpoint. With this, we can finally write programs such as the one presented in the introduction. The crux of obtaining the specifications of these protocols is the following channel endpoint ownership, which simply wraps the original channel permission with the reference corresponding to the imperative implementation. We can then get the following specifications, which is a slight variation of the aforementioned functional specifications, where we simply update the channel endpoints instead of passing around this channel continuation. Now note that these specifications are exactly the actual specifications of the original Actress paper, thus achieving our goal. Now these specifications can quite easily be proven with trivial reference reasoning. Now, as for the crescendo of this talk, we can finally prove the example of the introduction by picking exactly the protocol that we specified in the introduction, which we have now seen fully derived throughout this so far 20-minute talk. We can in fact also prove our program using the presented specifications, first using newchan to get two separate channel ownership, and then following the rest of the protocol by sending over this reference ownership. To wrap up, I will just briefly cover some of the additional features of this mini Actress approach to Actress. We additionally have recursive protocols. We also have variance protocols in which we, for instance, can choose to receive integers instead of natural numbers. And we have a notion of channel deallocation, both some traditional approaches in which we have symmetric and asymmetric coordination between the two endpoints, and a new variation in which the final send will also initiate a deallocation of the channel dynamically. Finally, I've not been able to touch too much on this nice cock mechanization, but if you read our paper, you might notice these small gears where you can click them and they will take you immediately to the corresponding cock mechanization. To conclude, I want to just briefly compare this work with the existing Actress work. We have now arrived at mini Actress, which sports a variety of different features. And in fact, this version of Actress supersedes the original work of Actress, which have been later dubbed Actress 1.0, even without employing any of the heavy cannons, the heavy machinery. However, it should be noticed that this heavy machinery was later put to work in subsequent work, Actress 2.0, which beyond mini Actress achieved so-called asynchronous subprotocols and a language generic approach to dependent separation protocols, which is called the Actress ghost theory. The latter of which was also put to work in the distributed setting in some other work that was presented yesterday here at ICFP, which you may check out if you're more curious about Actress. Finally, to conclude, it seems that there is a very strong, nice correspondence between sessions and higher order separation logic. We have achieved this mini Actress, which is a separation logic proof for verifying message passing programs. We achieved this in 3 layers: one-shot channels, functional channels, imperative channels, and proved simple soundness proofs with nested invariants. We obtained a bunch of protocol features and mechanized the whole thing in less than 1,000 lines. Now, some outstanding question is whether this is simple enough to incorporate in separation logic courses. And I mean, I would already bet that something very similar to the one-shot channels do exist in courses throughout the world, And at least based on what you've seen today, the session channels hopefully seem within arm's reach. And with that, all I have left is to say thank you, and then I will recursively take your questions according to this protocol. Thanks.
All right, we should have plenty of time for questions.
Hi, Simon Fowler, University of Glasgow. I've got two, if I may. So the first one is, well, first I want to say lovely work. It's really nice and a really lovely talk as well.
Thanks.
There was some work in 2017 by Alceste Scalas, Ornella Dada, Reihu, and Nobuko Yoshida about a similar encoding to the Kobayashi and Dada work, but in the multi-party setting. I was just wondering whether you think that your approach will scale to that.
I must have to admit that I'm not closely familiar with this work. Hopefully at least implementation-wise solution should scale, but one problem that we're facing currently in the Actress line of work is that multi-party session types are very difficult in the presence of these dependent binders. So at least the conjecture is that this stuff might be possible, but will possibly also have additional work to be figured out.
Okay, thanks. And the second question was, just early on in the talk, I was kind of uneasy about the spinning implementation of the one-shot channels. I'm just wondering whether whether that is problematic in practice, and whether, if so, whether there are any better ways of doing it.
Right. So, for what it's worth, like in the iris setting, we usually mostly consider partial correctness, right? So non-terminating programs are fine, which is why we allow ourselves to be spinning. We, in this work, do not have any proof of like deadlock freedom and stuff like this. So we mostly just hope that people write proper programs. However, we have made some subsequent work on this, where we take a similar approach to this and actually obtain deadlock freedom, in which we instead have a non-looping variation.
Brilliant. Thank you ever so much.
Thanks.
All right, are there any other questions? All right, if not, let's thank Jonas again.
It's always fun when you can't hear the clapping. I at least expect there's some clapping. All right, thanks.